You know when you look at computer code and it just seems like this completely foreign language? Well, what if I told you that you already think like a programmer every single day? We're going to break down how something as simple as making a cup of tea can show you the programmer that's already inside you.
Seriously, believe it or not, we all follow these little programs in our daily lives without even noticing. To prove it, let's start with a task that I bet is part of your everyday routine.
So, let me ask you, how do you make a good cup of tea? Take a second and really think about it. What are the exact steps you follow from the very beginning to the very end?
Okay, so you probably thought of something like this. You put the tea leaves in, pour the hot water, add some sugar, and give it a good stir. But wait, here's the really important part that makes it just like a program. You taste it. And if it's not sweet enough, what happens? You don't just give up. You go back, you repeat a step, you add more sugar, and stir again. That little decision, that loop, is pure programming logic.
And there it is. You've just created what programmers call an algorithm. I know, it's a fancy word, but all it really means is a list of steps to solve a problem. The problem was, I want a cup of tea, and your algorithm was the recipe to make it happen. See? Simple.
All right, now that we know what an algorithm is, let's look at its three basic parts. Every single task, whether it's making tea or launching a rocket, can be broken down into these three building blocks: input, process, and output.
Let's use another super simple example to see what I mean. Think about preparing a letter to post. This classic task is actually a perfect way to see these three building blocks in action.
First up, you have your input. These are just the raw materials, the stuff you need to get the job done. For our letter, the inputs are pretty obvious, right? You need paper, a pen, an envelope, and of course, a stamp.
Next, you've got the process. This is your algorithm, your set of steps. In action, it's the doing part. For the letter, the process is writing it, folding the paper just right, putting it in the envelope, and sticking the stamp on.
And finally, what do you get at the very end? Your output, the finished product. In this case, it's a letter that's all sealed up and ready to go in the postbox. So just remember that. Input, process, output. It's the fundamental recipe for solving any problem.
Okay, so here's where it starts to get a little more interesting. Just like in your own life, in programming, there's almost never just one way to solve a problem. You almost always have choices.
This is a perfect example. Imagine you're on your way to school, and your bus just breaks down. You don't just sit there and give up, right? Of course not. Your brain immediately starts thinking of other options. Maybe you can walk, maybe you can catch a different bus, or maybe you can call home and get a ride. All of those are different solutions to the same problem. I need to get to school.
Programmers actually have a name for this. They call it the solution space. And all that means is it's the collection of all the possible ways to fix a problem. You see, anyone can find one solution, but a good programmer looks at all the options to find the best one, the fastest or the most efficient.
Let's take a simple math problem, like finding the perimeter of a rectangle. You could do it by adding length plus width plus length plus width. That works. Or you could do length times 2 plus width times 2. Or you could add the length and width first and then multiply the whole thing by 2. See? 3 different processes, but they all give you the exact same correct output. That's the solution space in action.
So we have our steps, our algorithm, but how does the computer know which order to do them in, or when to make a choice, or when to repeat something? Well, that's where something called control structures come in. Think of them as the traffic rules for your program.
The first one is called sequence. This is the most basic one, and it's exactly what it sounds like. The steps are done one after the other in a strict, predictable line. You do step 1, then you do step 2, then step 3. No jumping around, no going backwards.
A perfect real-world example is just climbing a staircase. To get to the top, you have to take the first step, then the second, then the third, all in order. You can't just magically appear at the top. That's a sequence.
Okay, next up we have selection. Now this one is all about making a choice. Think of it like a fork in the road for your program. Based on whether something is true or false, the program will go down one path or the other.
Let's say you're in a bookshop. The big question is, do I have enough money? If the answer is yes, then you can buy the book. If the answer is no, then you can't. Your brain makes a selection based on that condition.
And our third and final structure is repetition.
As the name says, this is for when you need to do the same job over and over and over again. Programmers usually call this a loop,
where you repeat a set of steps until some condition tells you it's time to stop.
Think about a teacher taking attendance in class. They call out a name and they mark present or absent. Then they do the exact same thing for the next student, and the next, and the next. They repeat that simple process, that loop, until they've gone through every name on the list. That's repetition.
And here is the amazing part: sequence, selection, and repetition. That's it. Every complex app on your phone, every video game you love to play, is just built by combining these three simple ideas. Now that you know them, it's time to put your new programmer brain to the test.
So here's a fun little challenge for you. How would you go about making a kite? Using the ideas we just talked about, how would you break down that problem?
The key is to think about it systematically, like a programmer. First, what are your inputs? Well, you need things like paper, sticks, maybe some string. Then, what's your process? That would be your step-by-step algorithm for cutting and tying and gluing everything together. And finally, what's the output? A finished kite ready to fly. This way of thinking, breaking down big problems into small, logical steps, that's the real secret to programming. Now, what other things in your day can you see as an algorithm?
Hey everyone, and welcome. When you think about making a piece of software, you probably picture someone typing code like crazy, right? Well, that's not where it starts. It all begins with a plan. A really good plan is the secret sauce that saves a ton of time, stops bugs before they even happen, and honestly, it's how you build something that actually works. Today, we're going to pull back the curtain and look at the blueprints that coders create before they even think about writing code.
So let's start with the big question. A computer is incredibly fast and powerful, but it's also, well, kind of dumb. It only does exactly what you tell it to. So how do you make sure your instructions are crystal clear, perfectly logical, and are actually going to solve the problem you need to solve?
The answer to that is something called an algorithm. And don't let the fancy words scare you. An algorithm is just a recipe. Seriously, it's a step-by-step plan for getting from point A, the problem, to point B, the solution. Every single app on your phone, every website you visit, it's all built on a foundation of these recipes. Now, to make that recipe, that algorithm, super clear and easy for anyone to follow, you need a blueprint. You wouldn't build a house without a blueprint, right? Same idea. A programmer designs the logic first, then they start building.
And that brings us to the two main tools for this job. You can think of them as two different ways of writing down that blueprint. One is visual, for the people who think in pictures and diagrams. The other is text-based, for those who like to write things out in lists. Both get the job done, making the logic easy to understand before it's turned into actual code.
Let's start with the visual one. How do you literally draw your logic? Well, you use a flowchart.
A flowchart is exactly what it sounds like. A chart that shows the flow of your program. It's a diagram that lays out the whole process, step by step, using a set of special, standardized symbols.
And these symbols are like a universal language for programming logic. Ovals always mean start or end. A parallelogram is for getting input from a user or showing them an output. Rectangles are for doing work, like calculations. And maybe the most important one is the diamond. That's where your program has to make a choice. And of course, the arrows just point you in the right direction.
The most basic flowchart structure is just a simple sequence. It's a straight line. It starts, it does something, it does another thing, and then it ends. No detours, no choices, just a simple linear path from beginning to end, like this one for finding the area of a circle.
But let's be real, life is rarely a straight line. What if your program needs to make a decision? That's where the selection structure comes in. You see that diamond shape? It asks a question, like, is the remainder 0? And that creates a fork in the road. If the answer is yes, the program goes one way. If it's no, it goes another. This is the heart of how programs make choices.
And finally, we have repetition, which is a fancy way of saying a loop. Now look closely at the arrows here. See how the yes arrow goes back up to an earlier step? This creates a cycle. It tells the program to repeat a set of actions over and over and over again until some condition is finally met. It's incredibly powerful for processing lots of data.
Okay, so that's the visual blueprint. But what if drawing's not your thing? What if you'd rather just write it out? Well, that's where our second tool comes in, pseudocode. Pseudocode is pretty much what it sounds like. Pseudo means fake, so it's fake code. It's a way to write out your algorithm steps using plain, simple English. But here's the key, it's superpower. It is not a real programming language. This is awesome because it means you can focus 100% on the logic of your solution, without getting bogged down in annoying syntax rules like way to put a semicolon. You solve the problem first, then you worry about the code.
And it uses a bunch of really intuitive, common-sense keywords. You've got words like read for input, display for output, and calculate for doing some math. And you'll notice keywords like if, then, else for decisions, and while or repeat for loops. See? You can already see how these match up with the flowchart symbols we just talked about.
So, we've got the visual flowchart and the text-based pseudocode. They look completely different, but they have the exact same goal: to define the logic of a problem so clearly that there's no room for confusion. Let's actually put them side by side. Okay, remember this flowchart for checking if a number is odd or even? We get a number, we do a calculation, we hit that decision diamond, and then we show the result. It's a nice, clean, visual path.
Now check this out. This is the exact same logic, but written in pseudocode. The read number part, that's our input parallelogram. The calculate remainder, that's our process rectangle. And that whole if, then, else block, that's a perfect match for the decision diamond and its two branches. See? Same logic, just a different way of showing it.
So let's just recap that really quick. A flowchart is visual. It literally shows you the flow of control with symbols and arrows. Pseudocode is text-based. It describes that same flow using simple English keywords. Two different languages telling the exact same story.
All right, let's try something a little more complex to really see the power of planning. This is the pseudocode for a program that reads 10 numbers and then calculates their total and their average. It's starting to look a bit more like real code, but remember, it's still just our logical plan.
So what's going on here? First, we have to set up our variables. Think of them like little empty boxes to hold our numbers. We set our total and average to 0, and we create a counter, n, and start it at 1. Then we hit that while n less than 10 line. That's the boss of our loop. It says, hey, keep doing the following steps as long as our counter n is 10 or less.
And this diagram shows exactly what's happening inside the computer's memory. Let's walk through it. Okay, first time in the loop, n is 1. We read a number, let's say you type in 12. The total, which was 0, now becomes 0 plus 12, so it's 12. Then n goes up to 2. The loop starts again. This time you type in, say, 15. The total gets updated, it becomes the old total, 12, plus the new number, 15, which is 27. And this cycle just keeps going until we've done it 10 times.
And really, that's the whole takeaway here. It doesn't matter if you're a drawer or a writer. Whether you're using flowcharts or pseudocode, the goal is exactly the same. Create a clear, foolproof blueprint for your code. This is the stage where you find mistakes in your logic, where you simplify your ideas, and where you make sure your plan actually works before you get lost in the weeds of a real programming language.
So, I'll leave you with a final thought. You now have the tools to design a step-by-step solution to pretty much any logical problem you can think of. It could be for making a budget, for sorting your music collection, anything. So what's the first problem you would map out? Thanks for tuning in.
You know that feeling, like programming is some kind of secret club and you don't have the password? Well, guess what? Today, we're not just cracking the code, we're going to demystify the whole thing. And we'll do it using something you probably do every single morning. So let's dive in. Okay, so picture this. You're trying to tell a robot how to make a cup of tea. Now, you can't just say, hey, make me some tea. Nope, it would just stand there. You have to tell it everything. Pick up the kettle, walk to the sink, turn on the cold water. Every single tiny step. That right there is basically programming. It's just you giving super specific instructions to a very, very literal robot, which is exactly what your computer is.
So where do we even start with our tea-making robot? Well, with the absolute first thing you have to do, right? Put the tea bag in the cup. It's simple, it's clear, and you can't really mess it up. Think of it like the first domino in a long line. Once you push it, everything else can start to happen in a perfect logical order.
Okay, so we've got our first step. Now, what happens when we string all those little steps together? Put the tea bag in, boil the water, pour the water. What we're really doing is creating a recipe. And in the world of programming, a recipe like this gets a bit of a fancier name. We call it an algorithm.
Whoa, okay. That definition on the screen looks pretty serious, right? But don't worry. Let's just break it down. Finite sequence? All that means is it has to end. You don't want your robot stuck in an infinite tea-making loop forever. And well-defined? That just means every step has to be super, super clear. No guessing allowed. So really, an algorithm is just a foolproof recipe for a computer. That's it. All right,
Before we even try to write this recipe in a language a computer can actually read, it's an absolute lifesaver to, well, draw a picture of it first. A map, a blueprint, whatever you want to call it. In programming, we call this a flowchart. And it is so useful because it lets you see the entire plan from start to finish so you can spot any problems before you've even written a single line of code.
So the first piece of our map is this guy right here, the rectangle. This is the process box. Think of it as the workhorse of your flowchart. It's where the action happens. It's a straight-up command. Pour water in cup. Simple, direct, no questions asked. Just a clear instruction to do something.
Okay, but here's where things get really cool. This diamond shape, this is a decision block. This is where our little program gets a brain. It asks a simple yes or no question, like, is the water boiled yet? And depending on that answer, our whole recipe can split and go down two totally different paths. This right here is the absolute heart of logic in programming.
Okay, so we've got our visual map, our flowchart. It's awesome, but a computer can't read a drawing. So how do we get from these shapes and arrows to something that looks more like computer language? Well, there's a middle step, a critical bridge called pseudocode.
So what is pseudocode? Honestly, just think of it like a structured rough draft of our program. It uses plain, everyday English, so you don't have to worry about all the picky stuff like semicolons or perfect syntax, but it's organized in a way that mimics a real programming language. It's the perfect middle ground.
And here's where it all clicks. Look at this. On the left, we've got our flowchart. See that decision diamond, water boiled, and how the no arrow loops right back around? Now look at the pseudocode on the right. See that line that says, while not water boiled, boil water? That's the exact same loop, just written out in words. It's a perfect one-to-one translation from a picture to text. This is that aha moment where it all starts to make sense.
All right, since we're starting to write things out, we got to talk about a little bit of grammar. I know, but trust me, it's simple. Just like English, programming languages have rules. There are rules for how you can name things, and there are special power words that the language already understands.
First up is something called an identifier, which is really just a fancy word for a label. I mean, think about it. In our tea recipe, instead of having to say the current temperature of the water in the kettle over and over again, we could just create a label for it, like water_temp. It's just a shortcut, a nickname for a piece of info we want to keep track of.
But you can't just name these labels anything you want. There are a few simple rules, and they're all there just to avoid confusing the computer. For example, total_NOS, totally fine. But average marks with a space in the middle, nope, that's a no-go. Names also can't start with special characters like a $sign, and they can't start with a number. So 9A is out. It all boils down to one thing, being super clear.
Okay, next up we have reserved words. Now, if identifiers are the nouns, the labels for things, then reserved words are the verbs. They're the action words. They have special built-in meanings that the programming language already understands. Words like if, then, and while. And because they're so important, they're reserved. You can't use them as your own labels.
Here's a quick look at some of these reserved words from a language called Pascal. Don't worry about memorizing them all, but just notice a few. We've already seen while, right? And you can probably guess what words like if, else, begin, and end do. These are the fundamental Lego bricks we use to build the logic that we first sketched out in our flowchart.
All right, we have officially mastered the art of making tea with code. That's pretty awesome. But now, let's take everything we've just learned and apply it to a more, classic computer problem. This will show you just how universal these ideas really are.
So here's the new challenge. Find the larger of two numbers. And what's wild is that the logic is exactly the same as making tea. Seriously. First, you need your ingredients, right? In this case, two numbers. That's our input. Then, you have to make a decision. Is the first number bigger than the second? And based on that yes or no answer, you get your result, your output. See? It's the same pattern. Input, process, output.
And check this out. Here's the proof. On the left, you've got the flowchart for this number problem with its shapes and arrows. On the right, the pseudocode. And look, it's using those reserved words we just talked about, if, then, else, to spell out the exact same logic. The problem is different, but the thinking, the process, it's identical. And that's the key. Once you get this flow, you can solve almost any logical problem.
So from making a cup of tea to comparing numbers, what have we learned? That programming really just boils down to one thing: taking a big problem and breaking it into a series of tiny, logical, crystal clear steps.
So I've got a little challenge for you. Think about your own morning routine. Getting out of bed, brushing your teeth, picking out clothes. What's the first step? What decisions do you make? Try drawing a little flowchart for it. I promise you'll be pretty surprised to realize you've been thinking like a programmer this whole time.
Children, get this infographic card appears on the screen now and the short note related to this section for free. Join our WhatsApp channel from the link in the description box or comment section.